All right, so we are starting Unit 10, which is waves and sound. But the first half of this is Chapter 19, which is vibration and waves. So we'll look at some various topics, to explain how vibrations happen. So things like simple harmonic oscillators, pendulums. We'll start to describe the aspects of a wave, wave speed, the types of waves, so transverse versus longitudinal, how they interfere, talk about things like standing waves, and eventually get into something called the Doppler effect. So an oscillation is kind of this back and forth motion. So anything goes back and forth and back and forth. So like a child on a swing, that's an oscillation. Another example, pendulum inside of a grandfather clock. It goes back and forth and back and forth. So basically any motion that's going to repeat itself over and over is referred to being periodic motion. Okay, and periodic motion means it has some period, t, which is the time required to complete one full cycle of the motion. Okay, so theoretically, things that go around in a rotation could have a period of rotation. So like the orbit of a planet, there's a period of orbit for a planet, or like a period for a pendulum. There's also frequency, which is the frequency of those oscillations. So we think of frequency normally as things like radio frequencies. Okay, and those are in hertz, which is the opposite of a period. It's cycles per second. And we use capital H, lowercase z to represent that. Again, frequency and period are the inverses of each other. So the frequency is 1 over the period. So where period is in seconds, because it's really seconds per cycle, the frequency is in cycles per second, or the hertz. So just some examples of common periods and frequency conversions. So the hour hand on the clock, okay, so the hour going around, has a period of 43,200 seconds. So in terms of its frequency, that's 2.3 times 10 to the negative 5 hertz. Okay. We get down to the human heartbeat. So the human heartbeat beats about once per second. So its period is 1 second per cycle. Its frequency then would also be 1 cycle per second, or 1 hertz. Something like a computer processor. Lots of computer processors now are in gigahertz. So giga is like 10 to the 9th hertz. So 3.2 gigahertz would be a computer processor. If I convert that into period, that's 3.1 times 10 to the negative 10th seconds per cycle. That's really, really fast for one cycle of a calculation to be done. The most crude or basic example of periodic motion is a mass attached to a spring. So this is called the simple harmonic oscillator. So if we take a mass, attach it to a spring, and we pull it off of something called equilibrium. So equilibrium is that point where all the forces balance out. Well, all of a sudden now, there's going to be this restorative force that wants to push or pull that mass back to equilibrium, back to that center point, 0. Okay? So we can observe this and explain this motion as causing simple harmonic oscillations or simple harmonic motion. So here's what happens. We start out kind of way over here at some amplitude A. All right? So I've now given it energy. Okay? It's stored energy in the spring. Okay. We let it go. Whee! It starts moving. It now gains kinetic energy. So by the time it gets here, at a displacement of 0, it's got kinetic energy. It's in motion. It's moving. All right. Then it moves past there because it has inertia. All right. And it gets all the way over here to the far right, where, again, the force is now going to be stopping the mass, and it stops, hits the brakes. All right. And that's going to be like at a negative displacement. Okay. So now we've decelerated to that point. We start moving back the other way because that force now wants to accelerate the object. All right, so we get back to the middle here. Whee! I'm moving back. And then I eventually get all the way to the other side, and I've now completed a full cycle. And if I kind of look, I've got this like curved shape that starts to form here as I complete the full cycle. All right, the time for that oscillation would be the period, t. All right. So it takes a quarter of a period to do each of those actions. So to go from here to here, that was a quarter of the period. To go from here to here, that was a quarter of the period. Here to here was a quarter of the period, and then here back was another quarter of the period, with this whole back and forth motion. So I can actually plot this. So really, old system they used to do is they'd have these masses and oscillators, and they'd run a roll of paper behind it, and there'd be a little marker on the end of that cart, or a little pen, and it would trace out the function or the actual motion. And it makes like this sine wave or this cosine wave. And we would see the amplitudes. We could actually see that peak to peak between the amplitudes as the period, because the time between the peaks of the amplitudes is that period. The equilibrium position is in the middle there. And also, in the same note, we could say that the time here to here, that's also the period, between the negative displacement to the negative displacement maximum. So again, like I said, the easiest way for us to think about this is in terms of energy. So at a displacement of A or at negative A, it's only got spring potential. When it's at a displacement of 0, it's only got kinetic. And it's any point in between, it's got a little of each, a little spring, a little kinetic as it moves through. So we can analyze this in terms of all the stuff we learned about conservation of energy. And if we do that, and we go through all this, and we'll take some time in class to do this, we end up with this equation. We end up that the period is equal to 2 pi, right? And the 2 pi comes out of kind of some connections to circular motion, the square root of the mass over the spring constant, all right? Again, this is coming out from, dividing out all kinds of things, so dividing out the maximum amplitudes and all this stuff from the energy equations. But we end up that the period is equal to 1 over 2 pi, the square root of m over k. But remember, we know that the frequency is the inverse of that. So frequency ends up being 1 over 2 pi, the square root of k over m. And again, that's just coming from the fact that frequency is the inverse of period. So I basically just flipped everything. Other than the restorative force coming from a spring, right, something wanting to pull it back towards an equilibrium, we could rely on gravity to provide that restorative force, and that's what a pendulum is. So the simplest form of a pendulum is just some mass attached to a very light string or rod of mass L. All right, we generally call that mass a bob. Okay, so you may have heard of the term plumb bob before. Plumb bobs are a type of pendulum almost that are used in civil engineering to find a straight, true line down through the earth at a given point. But for a pendulum to be a pendulum, we have to have a very small angle of displacement. So I can't like pull this off here, to a large angle. Large angle is bad. Okay, so it's no. Theta has to be less than 10 degrees. All right, and the reason for that is something known as the small angle approximation. Okay, hopefully you'll learn about it in math class, but basically what happens is at very small angles, the sine of theta is approximately theta, okay, in radians. So if you ever want to prove this yourself, take the sine of 1 degree or 2 degrees, the degree value, and then find out the radian value of 1 or 2 degrees. And you'll notice the numbers are almost identical. And that's because of this small angle approximation. So those angles less than 10 degrees, you can basically say the sine of theta is basically theta for those small angles, less than 10 degrees. And when we go through the math, we find out there's a restorative force keeping it kind of going forward, and that restorative force is right here. Okay? That mg sine theta, that's what pulls it back towards equilibrium. All right? But at the very small angles, mg sine theta just becomes mg theta. And it allows us to do this really nifty little bit of math. And again, we get an equation that looks similar to the simple harmonic oscillator. Just now, our period is 2 pi the square root of L over G. So that means the frequency here becomes 1 over 2 pi the square root of G over L. All right? So that means that the period of a pendulum is affected by the local gravity. So this is why if you've ever looked at a grandfather clock, there's always this little tiny nut or knurled acorn looking nut at the bottom that's used to adjust the length slightly, and that's so you can affect the actual period by changing the length ever so slightly for your local gravity. Because if I put that clock here in New England versus putting that clock in California or at the North Pole, the period would vary just so slightly, and we have to be able to adjust for that. One thing we figure out here, though, is why does the length of the pendulum affect the period? Well, if it's the same angle of displacement, but a different length, we notice something here. From here to here versus from here to here, right? You have a greater distance that it has to cover with that longer pendulum period, right? So again, that's why it ends up being the square root of L over G. because you end up with a longer path that you have to cover with that restorative force. So same force, same acceleration over a longer period means it's going to take more time to cover that path. That's why the length affects it. Okay? But the mass doesn't affect it. And that, again, we can show in class when we do the derivation of that equation. So here's a quick check-in. We have a 1 meter long pendulum that has a 1 kilogram mass. Now suppose we replace that bob with a 2 kilogram mass. How will the period of the pendulum change? Will it double? Will it half? Will it remain the same? Or there's not enough information? It's going to remain the same. Because again, the period is T equals 2 pi square root of L over G. Mass is not in the equation at all. Okay? So now we have a 1 meter long pendulum with that 1 kilogram mass, but we now change the string that's tied to. And we now double that length 2 meters. So how will the period of the pendulum change? Will it increase, decrease, remain the same, or we don't have enough information? And again, it will increase because we're dealing with the square root of L over G. So square root of 2. It'll increase by a factor of the square root of 2. So this brings us into waves. So as we saw before, if I take and plot that oscillator over time, I get a waveform. So we start to give names to pieces of this. So I have the amplitude, which is from that equilibrium to that maximum displacement. Okay. Then I have the wavelength. The wavelength is the distance measured kind of peak to peak. Okay. Or it could be crest to crest, or it could just be any two random points that are that same point in the cycle. All right. So if you notice that bottom wavelength there starts at some random point as I'm going up, and it goes to the next random point where I'm going up. That's the same kind of distance away. So the key characteristics here of these vibrations are we have to have crests that are the high points and troughs that are the low points. Okay, just like with ocean waves, we get crests and troughs. Okay, the amplitude, that's the distance from the midpoint or the equilibrium point to the crest or to the trough. The wavelength, again, is the distance from the top of one crest to the top of the next crest, or just the distance between two successive identical parts of the wave. When we think of vibrations, normally we start to think of them in terms of frequency, not so much period. And again, getting a little back where we get this from, the Hertz, it comes from Heinrich Hertz. So he did a lot of the research in these oscillations and these vibrations. So basically frequency is specifying that number of to and fro vibrations are given a certain amount of time. So the number of waves passing any given point per second. So we're counting the actual number of waves we see. So 2 vibrations in 1 second would be 2 hertz. 3 vibrations in 1 second would be 3 hertz. Period, again, is the time to complete one vibration. So if a pendulum did 2 vibrations in 1 second, frequency is 2 hertz. The period, though, wouldn't be 2 hertz. It'd be 1 second divided by 2 vibrations, which is a half of a second. And again, just as a reminder, period is the inverse of frequency, and frequency is the inverse of period. So a key thing about waves is they actually transport energy, not matter. So when you see an ocean wave, it's not actually moving all that water. It's just energy moving through the water is what you're seeing. So all the water is, it's mixing down at like the atomic level a little bit, but I'm not moving, millions of gallons of water, across the ocean. I'm just moving the energy through it. So imagine like people being in line and somebody in the back of the line pushes the person in front of them. All the people don't move to the front of the line, but that push gets moved through the line. So wave speed is going to describe how fast that disturbance moves through the medium. And the wave speed can be found by taking the frequency and multiplying it by the wavelength. And for wavelength, we're going to use this very interesting little character here called lambda. Okay? It looks like an upside down Y. That's what lambda is. And that's how we're going to describe wavelength. So a wave has a wavelength of 10 meters, and the time between the crests is 0.5 seconds. We want to know what the wave speed is. Is it 0.1 meters per second, 2 meters per second, 5 meters per second, or 20 meters per second? And the answer is 20 meters per second. All right, and we get that because the frequency would be 1 wave or cycle in a half a second. Okay, so that's 2 hertz. And V is equal to lambda F. Our lambda is 10. Our frequency is 2. So that gives us 20 meters per second. So there are two types of waves. There's transverse and there's longitudinal. Okay. So the difference between them has to deal with how the actual material moves versus the energy that's transferred. Okay. So a longitudinal wave, the medium, okay, the material, vibrates parallel to the direction of energy transfer. So in this case, the energy is this way, and the actual medium is this way. All right. Whereas with transverse waves, the medium vibrates perpendicular to the energy transfer. So again, here, energy is still this way, but our medium is going up and down. Okay. And again, up there, that's back and forth too. So now waves can kind of start to interact with each other and get wave interference. So when two or more waves kind of meet and interact at the same time or same place, we call that wave interference. And we follow this thing called superposition, which you may learn about in math when you take and add two sine functions or two cosine functions together. All right. And this is kind of that displacement due to the interfering waves. You've probably observed this if you've ever seen two ripples in water and you see how they make an interesting pattern as they interact. That's this idea of wave interference or superposition. And there's two ways that they can interact, constructively or destructively. So in constructive interference, two waves, they meet, they're in sync with each other, so that means their peaks line up, their troughs line up, so their crests and troughs, and it basically makes a stronger wave. All right. Then there's destructive interference. So the peaks line up with the troughs line up with the peak, and they cancel each other out. All right. So there's real-world applications of this. All right. So a lot of surround sound systems work based on this. You've got multiple speakers in the room, and they use constructive and destructive interference to make it sound like an object is somewhere in the room. All right. Another application, noise-canceling headphones. They basically pick up the noise that's in the room and then play back the exact opposite wave to cancel the two sounds out, so it sounds like, or doesn't sound like, I should say, if there's anything there. It weakens the actual sound in the room. So now, to form a lot of waves, we get things called standing waves. So with a standing wave, you normally have kind of some fixed points for the wave. And those fixed points are called nodes. So they're areas of the wave where there's minimal or zero displacement, okay? So there's almost like zero energy to the wave at those points. Okay, the energy kind of passes through those points onto the next piece of the material without making it move significantly. Then there's antinodes. Those are the regions of maximum displacement or maximum energy. All right, and they should occur equally spaced from each other, the nodes and the antinodes. So when this occurs with a standing wave, our wavelength for the most basic form should be equal to kind of twice the string length, because our most basic one would look something like this. I could have it fixed at two ends, and I pluck it, and these two ends it's attached to can't move, but in the middle it can move. So this is like a guitar string. So now we already know that technically V is equal to lambda F. So I can rearrange and say that F is equal to V over lambda. But if lambda is twice the actual string length, we get to this version of the equation where that first harmonica, that fundamental frequency of a standing wave is equal to the velocity of the wave divided by 2 times the length. Okay, and we kind of use this to, in the project to figure out the standing waves for the strings, okay, as an example. Now, we're not just going to be limited to a single kind of pair of nodes and antinodes. We could have it set up that you've got, additional antinodes and nodes. We can add an extra antinode node, and we get the second harmonic, okay? And with the second harmonic here, lambda is equal to L. Or we could again add another. And in that case, we end up that this relationship of lambda and L, well, I basically started out with here, lambda was equal to 2L. Then we had lambda equaled L. Well, in the next case, I'm going to be able to fit 3 of these half wavelengths in the full length. Okay? So if I have 3 half wavelengths in L, that means that lambda is equal to 2/3 of the length. Okay? And we start following this pattern. All right, and the pattern actually is, okay, that lambda, I'm going to write it up top here in black, lambda is equal to 2 over n times L, whether it's the first, second, third, fourth, fifth harmonic. That kind of is the pattern that we're following. So again, just to kind of reiterate, so when we have that plucked string with the fixed ends, those are the nodes, the antinode is in between. Okay. And these additional second harmonic, third harmonics can set up on the string just because that string can resonate, which we're going to talk a little more about resonance later, can resonate on that same string. It means they can fit in the string. So what's happening here is the first harmonic is formed by the wave that reflects back and forth between the ends of the string. Okay, when the frequency is just right, that reflected waves interferes constructively to form the standing wave. Okay, and when it occurs at those multiple integers, right? We just talked about the whole integer piece of the first harmonic. We get these other different forms here. So in terms of the frequency, okay, if I want to do the math out with the frequency, that second harmonic is really twice the first harmonic, and we actually refer to that as the first overtone. Okay, so we're going to call this the fundamental, and we're going to call this the first overtone. Okay. Now the third harmonic will be 3 times that fundamental, but we're going to call that the second overtone. Okay. So for a string, if it's able to vibrate, so like on a guitar or a cello or a violin, it is going to have a fundamental frequency that's designed for it, but it will also have overtones and or you can think of it as harmonics that also occur at the same time. So that's why they all sound different. We can say that it's tuned to a certain frequency, but because they'll produce different overtones depending on the instrument, they sound slightly different. So to figure out the first harmonic or any harmonic of a standing wave, we end up with this equation that Fn is equal to n times v over 2L, where L is the length of the string, v is the velocity, that wave speed, and n is the harmonic number. Is it first, second, third, fourth, fifth harmonic that we're looking for?